Welcome to this structured Class 10 science lecture on metals and nonmetals. In our surroundings, we use a wide variety of tools, utensils, and structures. The electrical wires running through our walls, the steel beams supporting our buildings, and the copper pots in our kitchens are all made of metals. Conversely, the oxygen we breathe, the carbon in our pencils, and the sulfur in matches are nonmetals. Historically, human civilization progressed by mastering metallurgy. The Stone Age gave way to the Bronze Age, which was followed by the Iron Age. In this lecture, we will study the physical and chemical properties of metals and nonmetals, master the reactivity series, explore the formation of ionic bonds, examine industrial extraction metallurgy, and learn how to prevent the slow destruction of metals by corrosion. Metals possess unique physical characteristics that make them highly valuable for engineering and technology. First, metals in their pure state have a shining surface, a property known as metallic luster. Second, metals are generally hard, though this varies from metal to metal. Third, metals are highly malleable, meaning they can be beaten into thin sheets without breaking. Gold and silver are the most malleable metals. Fourth, metals are ductile, which is the ability to be drawn into thin wires. A single gram of gold can be drawn into a wire about 2 kilometers long. Fifth, metals are excellent conductors of heat and electricity. Copper and silver are the best electrical conductors, which is why copper is used for electrical wiring. Finally, metals are sonorous, meaning they produce a ringing sound when struck, which is why they are used to make bells. Chemically, almost all metals combine with oxygen to form metal oxides. The general reaction is metal plus oxygen gives metal oxide. For example, when copper is heated in air, it combines with oxygen to form a black layer of copper oxide. Similarly, aluminium forms aluminium oxide. Most metal oxides are basic in nature, as they react with water to form bases. However, some metal oxides, like aluminium oxide and zinc oxide, show both acidic and basic behaviors. These are called amphoteric oxides, and they react with both acids and bases to produce salt and water. The reactivity of metals with oxygen varies widely. Sodium and potassium react so vigorously that they catch fire if kept in the open, which is why they are stored immersed in kerosene. To organize metals based on their chemical behaviors, scientists developed the reactivity series. This is a vertical list of metals arranged in the order of their decreasing activities. At the very top of the series, we find highly reactive metals like potassium and sodium. These metals react violently with cold water, releasing hydrogen gas, which immediately catches fire. In the middle of the series, we have moderately active metals like zinc, iron, and lead. These metals do not react with cold water, but react with steam to form oxides and hydrogen. At the bottom of the series are noble metals like copper, silver, and gold. These metals are highly unreactive and do not react with water or dilute acids at all. The reactivity series allows us to predict displacement reactions, where a more reactive metal displaces a less reactive one from its salt solution. Why do metals and nonmetals react? They react to achieve a stable, completely filled valence electron shell, mimicking noble gases. Metals tend to lose electrons from their valence shell to form positively charged cations, while nonmetals tend to gain electrons to form negatively charged anions. The electrostatic force of attraction between these oppositely charged ions binds them together, forming an ionic or electrovalent compound. For example, during the formation of sodium chloride, a sodium atom loses its single valence electron to form a sodium cation. A chlorine atom gains this electron to complete its octet, forming a chloride anion. The attraction between sodium and chloride ions yields sodium chloride crystals. Ionic compounds have high melting points and conduct electricity when dissolved in water or melted. Ionic compounds exhibit distinct physical properties due to the strong electrostatic forces holding their giant crystal lattices together. First, they are crystalline solids at room temperature and are generally hard and brittle. They break into pieces when pressure is applied. Second, they have very high melting and boiling points because a large amount of energy is required to break the strong interionic attractions. For instance, sodium chloride melts at over 800 degrees Celsius. Third, ionic compounds are generally soluble in polar solvents like water, but insoluble in nonpolar organic solvents like kerosene or petrol. Finally, while ionic solids do not conduct electricity because their ions are locked in fixed positions, they are excellent conductors in molten or aqueous states, as the ions become free to migrate. Metallurgy is the scientific process of extracting pure metals from their naturally occurring mineral compounds, called ores. Ores mined from the earth are usually contaminated with large amounts of impurities like soil and sand, known as gangue. The first step is the concentration of, or to remove this gangue. Next, the concentrated ore is converted into metal oxides, which are much easier to reduce to free metals. For sulfide ores, we use roasting, which involves heating the ore strongly in the presence of excess air. For carbonate ores, we use calcination, heating the ore strongly in limited air. The resulting metal oxides are then reduced to free metals using carbon or highly reactive metals like sodium or calcium as reducing agents. The metals produced by reduction processes are often impure and must be refined to achieve high purity. The most widely used method for refining metals like copper, zinc, and gold is electrolytic refining. In this process, a tank is filled with an acidified copper sulfate electrolyte solution. A thick block of impure copper is made the anode, which is the positive electrode, while a thin strip of pure copper is made the cathode, the negative electrode. When electric current is passed through the electrolyte, copper ions from the electrolyte migrate to the cathode and deposit as pure metal. Simultaneously, an equivalent amount of copper dissolves from the impure anode into the solution. Impurities settle at the bottom of the tank below the anode, forming anode mud, leaving behind 99.9% pure copper at the cathode. Corrosion is the slow, progressive destruction of metals due to chemical reactions with air, moisture, and chemicals in their environment. The most common form of corrosion is the rusting of iron, where iron reacts with oxygen and water to form a flaky, reddish-brown hydrated iron oxide. Rusting requires both oxygen and water. If either is absent, rusting cannot occur. Other metals also corrode. Copper reacts with moist carbon dioxide in the air to slowly form a green coating of basic copper carbonate. Silver articles turn black after exposure to air because they react with sulfur compounds to form a layer of silver sulfide. Corrosion causes enormous economic damage, weakening bridge supports, vehicle bodies, and railway tracks globally. To prevent the enormous economic losses caused by corrosion, various methods are used to shield metal surfaces from oxygen and moisture. The simplest method is barrier protection, which includes painting, oiling, or greasing the metal surface. Another highly effective method is galvanization, which is the process of coating iron or steel with a thin layer of zinc. Even if the zinc coating is scratched, the iron remains protected because zinc is more reactive and corrodes, sacrificing itself. Other prevention techniques include chrome plating, anodizing, or alloying. Alloying is mixing a metal with other metals or nonmetals to change its properties. For example, mixing iron with chromium and nickel yields stainless steel, which is strong and does not rust at all. In this comprehensive lecture, we have explored the chemistry of metals and nonmetals. We analyzed physical characteristics like malleability and electrical conductivity and studied chemical reactions with oxygen. We navigated the reactivity series, showing how potassium is situated at the top and gold at the bottom. We examined the ionic bonding mechanism, where valence electron transfers form stable lattices. We dissected metallurgy, detailing roasting, calcination, and electrolytic copper refining. Finally, we studied corrosion and prevention methods like galvanization and alloying. Master these concepts and formulas to build a strong foundation in chemistry. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, You must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension.